So now at long last, it's really time to start focusing in on parallel streams. And we'll begin this discussion by talking about the transition from sequential to parallel streams. We'll begin also by talking about how you can reuse the same aggregate operations that you've learned to know and love with sequential streams and apply them pretty much without change, as long as you're careful in how you write your operations, using stateless behaviors, for example, in a parallel streams context. So just a quick recap, I'm sure you all know this by now, but a Java stream, be it sequential or parallel, is a pipeline of so-called aggregate operations that process essentially a flow or a stream of elements, which are also known as values or data. So we've looked at this before. We've looked at this in the context of several examples like the search stream gang example. In that context, the aggregate operations, which include intermediate operations and terminal operations, use internal iteration, and they use behaviors passed in as lambda expressions or method references to process all the elements in the stream. By default, streams execute sequentially. If you use the stream factory method or some variant of factory methods that work sequentially, all the aggregate operations will run their behaviors in one thread of control, typically whatever thread calls the terminal operation. Conversely, when a stream executes in parallel, it's partitioned up into multiple substreams or chunks that run in the common fork join pool. And you'll see that this gives you tremendous number of benefits with very little effort on your part to have to do much other programming to get the benefits of parallel processing. The threads that run in the common fork join pool, of course, can execute non-deterministically. That's the beauty of concurrency and parallelism. You don't know, you don't really care the order that they run in. All you care is that they run faster and you get the results back correctly and perhaps in the right order if that's what your semantics dictate in terms of how you've configured the various properties of the stream. The intermediate operations basically iterate over and process behaviors on the chunks in parallel. And it's always important to remember that things are pulled through the stream from the source to the terminal operation, basically from top to bottom, from left to right, as opposed to going from left to right, top to bottom. So it's kind of non-intuitive at first, but that's the way things work. And that implements an optimization technique known as integrated layer processing. Terminal operations are used to combine the chunks into a single reduced result when everything is finished. And as we've talked about many times before, if you use stateless behaviors implemented with lambda expressions or method references, you're going to get much better results. It'll be faster, and it'll also be more likely to be correct because you won't have to worry about corruption and race conditions and data visibility, consistency issues, and so on. Ideally, and if you follow the rules and use the stateless behaviors we'll talk about and some other things to keep in mind, you'll be able to make these changes to support parallel processing with only minuscule tweaks to your code, namely going from stream to parallel stream. What that means, of course, is that the same aggregate operations work just as well for sequential and parallel streams. So it's really apples to apples comparisons here. You don't have to go off and learn a whole bunch of new stuff. For example, as we will see here shortly, and as you probably already surmised from programming assignment 2B, you can use the same aggregate operations to do the sequential and parallel versions of things. So in the context of the case studies we've been looking at, the search with sequential streams code is virtually identical to the search with parallel streams code, except stream is replaced with parallel stream, but everything else is pretty much the same. Therefore, as we talked about before when we were talking about the benefits of streams and parallelism and when to apply parallelism, you can treat parallelism as an optimization that leverages the available cores. So that, again, is just kind of building on that earlier set of concepts and then showing how those concepts are realized in the context of the parallel streams framework. Now, of course, there's some things to remember, and if you don't remember these things, you'll get yourself in big trouble. But the behaviors that are run by the aggregate operations have to be very carefully designed to avoid accessing unsynchronized shared mutable data, which again is, as always, the root of all evil in programming. So if you have shared data that's mutable, in other words, it can be changed and shared, then you've got a world of things to think about. And we'll talk more about some of the common traps and pitfalls that arise when you do this and some ways to avoid it. The most obvious way to avoid it is not to have shared mutable data. But sometimes you can't avoid that, especially if you do things like caches, for example. But we'll talk about that in a few upcoming videos.